Okay.
Sleeping.
Let's get started here. This is my problem, review problem over the Washer method from lesson 7-3. Example, the region bound by the graph of y equals 6 natural log of x and y equals x minus 1 is rotated about the x-axis, find the volume. So first of all, let's get that graph so you can see kind of what region we're talking about. I want to make sure you have the right region before you actually start revolving it or rotating it around. So I turn on my calculator, go to y equals, type in 6 natural log of x, then type in x minus 1. Let's try just hitting zoom 6 and see what happens. So there's your natural log graph. Okay, so we can't quite see all of it, can we? So I bet this curves and crosses this line up in here. So let's make our x max a little bigger and our y max a little bigger. I don't think we need this area down here, so we can make our x min 0 and our y min 0. Let's try to x max of 15 instead of 10. Y min 0, let's try y max of 15. Oh, still don't have it. Looks like we gotta go further. Let's try 20 for the x max and 20 for the y max. Okay. So there's our shape. Let's sketch that. And maybe we want to get our intersection points too while we're at it. So second trace number 5 intersect. And let's get this one down at the bottom left-hand corner first. You might be able to look at the equations and figure these out, but I'm just going to use the calculator right now. 1, 0 is our intersection point down here. Now let's find this intersection point. Second trace, number 5. We get up, we push enter on the first curve, push enter on the second curve, and then push enter where we think the intersection is. So I'm just going to get up here close first though. So on my first curve, push enter. Now on my second curve, push enter. Now go where you want, where you think the intersection occurs. And there's our intersection point. Alright, let's sketch this out. The first drawing is going to be our two-dimensional drawing. Something like this. This is the point 1, 0 right there. This x-coordinate is 18.5. We're going to use the whole thing. And actually, let's store that number, okay? Because I don't want to have to write that number over and over, and I might miswrite one of the decimals. So one thing you can do to make this a little easier for yourself is push second quit, then push the store button, which is right above your on button, and let's call this B, alpha B. So alpha B, enter. Now every time I hit alpha B, the calculator knows that's the number I'm talking about. So let's say we're going to go from 0 to B. Somewhere let's write that down. Let's say B equals 18.5198. But we know that we've got that entire decimal stored there for B. Here's our region. The curved line is y equals 6 natural log of x. The straight line, y equals x minus 1. Now, we're going to revolve that around the x-axis. So we have to be able to visualize, if we take this region and spin it around the x-axis, what's that going to look like? So I got my drill today to maybe help us with that a little bit. Actually, this shape isn't quite the right shape, is it? Actually, if I do this, it would go around the y-axis, wouldn't it? Like that. It's not quite the right shape. In fact, let's change the problem to make it match. Let's go around the y-axis. That way it'll actually be this shape that we're seeing right here. You see that? So what's that look like as far as the three-dimensional shape? Like a cone? Is it a solid cone or is there room on the inside? Yeah, there's empty space on the inside there. Okay? So it's a cone with some stuff hollowed out, maybe kind of a funnel shape hollowed out in the middle. Alright? So I'm going to change the problem to match that. It's revolving around the y-axis. Now, how's that going to change? If I'm going to go around the y-axis, that's going to change how I reflect this. Because originally what I was going to do was take my shape, this shape right here, and and spin it around this way. Now I've changed the problem and go around this way. Okay, so now I'm going to reflect over the y-axis and look something like this. Reflect those curves over the y-axis. Let's draw that a little bit better. Something like that. Revolving around the y-axis. Alright. Now, the formula for the washer method is this. Volume equals pi times the integral. Anyone remember what comes next?
Big R squared minus little r squared.
Right. The large radius squared minus the lowercase radius, or the small radius squared. Anybody know how we find the small radius? We go from,
From the bottom.
well, we're going to go, this is our axis of rotation, the y-axis. We're rotating around that.
So then our equations will change, won't they?
Yep. Yep, they are. We're going to get to that in a second. But we're going to spin it like this. We're going to slice it. If our axis of rotation is vertical, we always want to, when we use a disk or the washer method, we want to slice our figure perpendicular to the axis of rotation. So we're going to slice it this way. So we're going to get this washer right here. The thickness of the washer would be right there. So the skinny dimension of the washer runs up and down. So is that a dy or a dx if it goes up and down?
dy.
Right, that's a dy. dy is this thickness or skinniness right there. So our first radius runs from here to here. First radius on this picture would be from here to there. That's our small radius, right there. Okay? And again, the skinny dimension runs up and down, so we have to use y's. That means our equations have to be in terms of y. So we have to rewrite these equations so they're in terms of y. We have to solve for x, in other words. So let's do that off to the side here. Y equals 6 natural log of x. So let's multiply by 1/6 on both sides. You get 1/6 y equals natural log of x. Trying to solve for x, how would I get rid of that natural log?
E.
Right, it's called exponentiating both sides. So e to the 1/6 y equals e to the natural log of x. E and natural log are inverses to cancel out. So you end up with x equals e to the 1/6 y. That's this equation right here. So I'm going to cross this off, call this x equals e to the 1/6 y. If I solve this one for x, what would I do to both sides? Add 1, right? So add 1 to both sides, you get x equals y plus 1. Okay. What's another name for the y-axis? What's the equation of the y-axis?
X equals 0.
X equals 0. So, to get this distance between that curve and the axis of rotation, I take right curve minus left curve. So I take e to the 1/6 y minus 0. That'll give me my small radius. So my small radius is e to the 1/6 y minus 0. Right curve minus left curve. To get my big radius, I want to go from the axis of rotation to the furthest curve. That's going to be my big radius. So what would I subtract to get my big radius here?
Y plus 1 minus 0.
Right, y plus 1 minus 0, which would just be y plus 1. So when the radius runs sideways, right curve minus left curve. If our radius ran up and down, then it'd be top curve minus bottom curve. Okay? Now, and we're using y's. We decided this was a dy right here. So our volume is going to equal pi times the integral. Our big radius is y plus 1 quantity squared then, minus our little radius, which is e to the 1/6 y squared. That's all times dy. Now my bounds. Would I want my bounds to be my x coordinates or my y coordinates?
Y.
Y, yeah. I was going to use, I started using x because I thought I was going to revolve it around the x-axis. But then I changed the problem and said, hey, no, let's revolve it around the y-axis, which is going to be a different figure. So now I need y coordinates. I need to go from 0, that's my lowest y coordinate, up to whatever this y coordinate is straight across from here. This will actually be my b. So let's go back to my picture again here. Back to my graph. Let's find that intersection again, second trace number, 5. Enter, enter, enter. And 17.509803. Might be really. And this goes from a y coordinate of 0. So you could store that if you want, or you could just type it in. It's up to you. So any questions so far? All right, let's go ahead and type it in now. See what we come up with. So second quit, Math 9, just finite integral, and type in.
Draw your pi out for.
You could, I'm just going to wait and put pi, multiply by pi later, but you could. That's a good question. You could put it in, but let's go ahead and do parenthesis. Now, I can't type in y, even though it says y, I have to type in x. So x plus 1, parenthesis squared, minus e to the 1/6 y. So e is second divide to the power of 1/6 y would be the same as y divided by 6. I'm going to write it that way. So it would be x divided by 6. Close your parenthesis, squared. Now I need to go comma x, comma lower bound, which is 0, comma my upper bound, 17.509803. Enter. So my answer is 1088.727 pi cubic units because it's volume. Or you could hit times pi and get 3,420.336 cubic units. So my volume again is, let's write this out, 1,088. You always go out 3 decimal places or more. 27 pi cubic units. Or you could write it as 3,420.336 cubic units. Any questions about that?
Okay, if we would have done it like you originally had it with the x-axis, it wouldn't even have been a washer method, would it?
It would be. Good question. He's saying, what if we would have taken our figure, grab a different color to show you, and rotated around the x-axis here. If we would have taken this and rotated this figure here, then it would look something like this. You've got kind of a bowl-shaped figure with a V cone hollowed out of the inside.
So if you just turn 90 degrees of the last image.
Well,
Yeah, but it wouldn't have been a washer, would it?
This-
Because you're touching them.
well, yeah. If you think about it, if you sliced it though.
Oh.
See, if you went to start slicing this up, you would get hollow space in the middle here. So you would get a washer. Anytime there's white space between your axis of rotation and your figure, if there's any white space in there, that's the washer method. So even if you rotate it around the x-axis, I see this white space, have to use the washer method. If I rotate it around the y-axis, I see this white space, got to use the washer method. When you have something like this, and you want to go around the x-axis, I'm going to take that around the x-axis. That's not going to be the washer method because you won't have any hollow space on the inside. That would be the disk method. But if I rotated this figure around the y-axis, I see white space here between the y-axis. Then that would be the washer method. So you're looking for that white space. If you see that white space, you know that when you rotate it, you're going to get some hollow area and hollow volume in the middle. Okay, good question. So this would still be, now this is not the same shape though, because notice the black one has straight sides and a curved inside. The yellow one has a curved outside and a straight inside. So you get a different answer. The yellow answer would be different than the black answer. All right?